Lx. Right? So this is the equation of the function or of the load or the distributed load. With this in mind, the equivalent load will be equal, you integrate omega naught over Lx dx 0 to L. So when you integrate this, you have what? Omega naught x squared over what? 2L bounded my limits L and naught, and this is equal to what? Omega naught L over 2. So this is basically the area of the what? Distributed load. Very clear. So straightforward, you don't need to do the integration. What do you do? Half base times what? Height. Very clear. Okay. So once you got the equivalent load, we know that this is omega naught L over 2. The distance from here to here, if this distance is x, the distance from here to here is what? 2x over 3, and the distance from here to here is x over what? 3. Why? Can someone prove this for me? Why is it 2x over 3 on the left-hand side and on the right-hand side x over 3? It's going to be a homework question. It can, yes. Well done. It's the centroid of the system. Okay, so it's not going to be a homework question. Okay. Right. So once you got that, I'm going to sketch the other equivalent load. Okay, so the other equivalent load. Now this is where you have to be really, really careful. So there's another, oh, wow. How did I do that? Not a clue. There's another distributed load over here. Okay. And the equivalent load, I'm going to shift this across. So the equivalent load will be equal to half. The base is L over 2. This is omega naught. Okay, so if we look at the distributed load, this is omega naught L upon 4. Over here, this is omega naught L over 2. Okay, and then the safest thing to do, okay, you have to be really organized. Okay, the distance from here to here, right? This distance from here to here is equal to 2/3 multiplied by L over 2. So this will be equal to what? 2/3 multiplied. So this will be L over 3. Okay, am I right? L over 3. Right. So 2/3 L. Okay. So we got all our distance sorted out now. Okay. So the next thing we are going to do, we are going to carry out static analysis. Okay. So the next thing we are going to do, we are going to carry out, we're going to perform static analysis. Okay. So static analysis that we're going to carry out is we are going to do dimension about moment at about z-axis at point B is equal to what? 0. Okay. So what we are trying to do is we are going to take moment at point B. Okay, we are going to take a moment at point B. So from here, we know that AY is going in a clockwise direction. So minus AY L. Okay. And then the equivalent load is going into a counterclockwise direction. So it's plus by omega naught L over 2 multiplied by a distance L over 3. Because the distance from here to here is equal to L over what? 3. Okay, does this look familiar to all of you? Yes or no? Right? It's just a refresher. I know some of you have done this maybe 2 years ago now. Yes or no? I'm going to help you to remember. So from here, the omega naught L over 4 is going to do a clockwise minus by omega naught L. Okay, minus by omega naught L over 4. Now we have to be careful with the distance now, right? So the distance from here to here, which I did not calculate earlier. So this over here is 1/3 L over 2. So this is L over 6. So we have determined that distance over there is equal to L over 6, and the whole thing is equal to 0. Okay. So we just need to tidy up this equation. So minus AYL, then plus by omega naught L squared over 6 minus my omega naught L squared over 24. So from here, we know that AY L is equal to omega naught L squared over 6 minus by omega naught L squared over 24. So this will be equal 1 over 6 minus 1 over 24, 1 over 8. So omega naught L squared over 8. And with this, we have concluded that AY is equal to omega naught L over 8. And if it's positive, okay, what we see is positive, our assumed direction is correct. If it's negative, our assumed direction is what? It's wrong. From here, we do the next static analysis is we are going to do summation about forces in the y direction is equal to 0. So from here, we will have AY minus by omega naught over L, omega naught L over 2, minus by omega naught L over 4, and then we have to plus by by, the whole thing will be equal to 0. So from here, we know that by is equal to omega naught L over 2 plus by omega naught L over 4 minus by AY be equal to omega naught L over 8. So half plus by a quarter minus by 1/8 is 5 omega naught L over 8. Okay, again, it's positive, and this is the condition. So now we have found two boundary conditions. Two boundary conditions. So boundary condition number 1 that we have found, then when x is equal to 0, right? AY is equal to omega naught L divided by 8. Now, boundary condition number 2, we have to be very careful. This is a reaction force when x is equal to L. By is equal to 5 omega naught L over 8. Okay. So mathematically, we have just determined our boundary condition. Anyone, any questions so far? So far it's clear, yes or no? Okay. So the next thing that we're going to do from here, we can determine our so-called shear force and bending moment at point B. Okay. Now, coming back to this diagram over here, I want to focus, okay, I want to focus on the boundary, on the moment boundary conditions. Okay, we are going to focus on the boundary moment, not moment, bending moment. I do apologize. Sometimes it's very clear, sometimes it's not so clear. Okay, I know for the fact that when you are doing 2P04, you don't have a lot of boundary condition on overhanging beams. Am I right? It's usually what? Simply supported and what? Cantilever. Okay. So what if it is what? An overhanging beam. So I'm going to look at overhanging beam first. Or let's do something simple. Okay, let's look at simply supported. Okay, this is like a revision. Okay, I hope you all can recall most of this stuff. If not, don't worry. But I prefer you to recall them. So when we have a simply supported beam, this is our point A, this is our point B. One side is pinned, the other side is on a what? On a roller. So if we have a transformation, X, Y, and over here, rotation about Z. And what is the difference is this. For this case, at pin, X motion is equal to 0, Y motion is also equal to what? 0. When that's the case, we know that AX is not equal to 0, AY is also not equal to what? 0. AX and AY determine the. Then at point B, what we realize that X is not equal to 0, but Y is equal to 0. Agree or disagree? Why is that? At point B, the beam is allowed to go what? Left and right. It's on a what? It's on a roller. How many of you have been under the bridge? Do you see rollers under the bridge? I repeat again. Do you see rollers under the bridge? Good. I will highly recommend you stop by a bridge, look under the bridge. I will highly recommend because I did not know. What do you see when you're under the bridge? You don't get to see rollers. Are we clear? Okay. If everyone says you can see roller, pardon my French. Oh, sorry. Bullshit. Sorry, pardon my Italian. If you go under a bridge, one side of the bridge will look like this. So this is our bridge. The other side of the bridge, you will just see this. And then that might be a gap. and then you will see a metal plate put on top over here. This is the same if we have a transformation over here, that this is x and this is y. This is the same as x is equal to 0, y is equal to 0, x is not equal to 0, y is equal to what? 0. Don't always believe what the professor says. Go and check it out. Are we clear? Just go under any bridge. Okay? If any bridge is built this way, if you see any bridge that is built this way, okay, built this way, what will you do? Don't cross that bridge on the top. Right. At one stage, the thing will what? Will crack. Crack where? Okay. Now, you can see now on the roller now, for this case, right? For this case, AX is equal to 0,